Okay, the next part is the AC generator, the alternating current generator. For some reason this has been omitted from your syllabus, I think, for this year. When they reduced the syllabus, they have not mentioned this, at least as far as I know, whatever I've seen tells me that this has been omitted. So that is why I am doing it as a separate video. But I think this is something that you need to know. So we'll talk about it, and I've not included this in that original video because this is not needed, is what they said. It's not needed for your exam. But it makes a lot of sense to understand this because this is something that you already studied in your 10th standard. We're going to expand on it. We're going to introduce a few equations into it, but that's about it. But pretty much this is something that you already learned, and we are going to explain to you how whatever you've learned so far fits nicely in this application. And without this, nothing will run in the world. So you need electric power to even do anything that you want to do. So it's very important that you know about the AC generator. So this is where all your power comes. Okay. Again, this as a magnet. In this case, I've got a permanent magnet here. It's a very simple generator. So like I've got a permanent magnet which will establish a constant field in in this gap. Okay. So this is North Pole, South Pole. So it's more like a horseshoe magnet or something. You can see that there is a field established between the poles. Okay, and you have a coil between the poles, and this coil will be rotating. And if I rotate this coil, then this coil will produce an EMF. Why? Because think about this. So the coil is like this. Suppose the coil, let me take this as a coil. Okay, so this is a coil. Okay, so suppose the coil is like this, and then the North Pole is here and the South Pole is here. So flux lines are going through that coil. Okay, we know that the flux has to change. Then how to change that flux? Because I said it's a permanent magnet. If it's a permanent magnet, then how to change the flux? Okay. If I move the coil, yes, I can do that, but then that's pretty cumbersome. Okay, it's not very easy for me to do. Okay? It will be oscillating, so I need to take it out and then take it in, take it out, take it in. That's not a very good thing to do. Okay. But what happens if I rotate it? If I rotate it, you see, right now, the phase of this coil has all it's full, right? Like it's full of all the flux lines from the magnet. Okay. Now, if I tilt it, notice that only so many lines are, passing through this. If it is vertical, then you see up till here, notice so much, flux like this. Okay, so much is passing through this. All the flux is passing through this at this height. But if I tilt it now, you notice now the height is reduced, so only so much flux will be passing through this. And if I tilt it further, then only so much flux will be passing through this. You see, I want you to imagine the height. And if I tilt it further, only the flux which is going through this is reducing. And if it is flat, if it's a single coil, okay, it's a single loop, if it is very flat, then there will be no flux that will go through the area of the loop. Okay, because it's flat now. Previously, if it was like this, it was vertical, it had maximum coverage. Now you're turning like a paper, and now it's like this. Okay? A paper like this. All the flux is going through it, and then like you're turning the paper, you see less and less flux is going through there, and then when it is dead flat, you see no flux, no magnetic line is going through this area because it's so flat. The lines are grazing that area, but they are not going through it. So zero flux lines will go through this area when it is dead flat like this. And when again it changes, then flux which is going through it is also changing. You see, it's like this. So you are effecting flux change through the coil by rotating it in a constant field. So when you do that, clearly an EMF will be generated. And we are going to calculate what that EMF will be in this case. And this is something that you may not have studied in your 10th standard, and that is what we are going to do now. That's the extra bit now. Okay. So let me just draw this. Okay, so this is the simplified version. Okay. So I have this magnet N and then S. Okay, and in this case I have the coil in the vertical position. So it is the vertical position. The coil is the vertical position. This coil is the vertical position now. Now all the field lines will go through it. The field lines go, everything will go through it. It's vertical. Okay. So now if I turn it like this, then what happens is that from this height it reduces to, let's see, now you see as I turn, then it makes a circle. So when it is here, see, from here, now I have only this. So in that case, how many lines will go through this? Only this, right? Only these will go through. Yes. You see, the blue ones are now less than the red ones. So blue ones are the new field lines. The red ones are the old field lines. Okay. When it was in this position, all of them were going through it. But when it is in this position, you see only so much is going through it. And when it comes dead flat, nothing will go through it. Nothing will go through that area. They will graze along the area, but nothing will go through the area. Okay? So zero flux will go through. So this is where you get maximum flux, and this is where you get minimum flux, zero flux. And again, when it turns the other side, then you get maximum flux, and when it comes like this, then you will get minimum flux. So you get maximum flux, then minimum flux, and then maximum flux, then minimum flux in one full cycle of this coil. Okay. So if the flux going through the coil changes, clearly an EMF will be induced. So now you need to have an expression for the flux through the coil. What is the flux through the coil? Let's say that B is the magnetic field intensity, the magnetic field strength. B is magnetic field strength. Now what is the flux through the coil at any point? So that is given by this B, which is a constant. B is a constant because it's a permanent magnet, constant field. So B is a constant now. And it is not moving, magnet is not moving, so it's a constant. What happens now? This, let's say, when it is in this position, when it is like this is the area, right? So this is the area of the coil, the area of the coil. So when it is in this position, all the area would be included. But when it starts turning, then the area which is getting exposed to this, to the magnetic field, is reducing, and when it is in this position, then it becomes zero. So the area is a varying quantity. The area is a varying quantity. So this is A. And I can assign a vector to it, right? Like B dot A. So B dot A vector. Okay, this from your previous videos. So now this will give you this thing B A cos theta. Because notice when it is here, when it is vertical, when the plane is like this, the normal is aligned with the field. Because when I talk about the vector of the area, then we'll take the vector of its normal. So when it is here, the vector of the area is like this. Okay, when this coil is vertical, it's like this. And in that case, the normal, the vector of the normal and the field will be aligned. So this is when you will have zero angle. When the coil is like this is when you will have zero angle. Okay, and when coil turns, then you'll have different angles now. Okay, it's like this. Sorry, it's like this. So this is when you will have zero angle. So as it turns, then you see the normal will be changing. If I assign the normal here to this like that, as it turns, you see the normal will also be changing. So the angle will be changing. So the area, the effective area exposed to this field will also be changing. Okay. So phi b is dA cos theta. So this is theta. This is theta. But what is theta? Suppose I rotate that with a constant angular velocity or angular speed, omega, then my theta is actually equal to omega to t. So if omega is the speed, angular speed, so many revolutions and so many degrees, or so many radians per second, okay? When I do that, that is my omega, then my theta at any point in time is given by this expression. So this is 0 when the coil is here, it is 0. The coil is vertical, but the normal is aligned with the field. So this is 0. But then it's going to turn, so it will take some time to make an angle, and that time multiplied by the speed will give me that angle. Okay? So my phi b from this my phi b is b a cos omega t. Okay, so this is effective area. A cos omega t is effective area. A is the area of the coil, enclosed with coil. But A cos omega t is effective area to the flux. A cos omega t. Okay. Now, if I have n turns in the coil, I've got one turn here. If I have n turns in the coil, then clearly, then the flux linkage would be n phi b, that is equal to n b a cos omega t. Then what's the EMF induced? EMF induced is equal to minus d n phi b by dt. Flux linkage. So it's going to be minus, I take this n out, and b is a constant, a is also a constant, there is no change in a. Okay, then what I'm going to get? I'm going to have d cos omega t by dt. And this will give me my E is equal to, if I differentiate cos omega t, then I'll get minus, let's say a minus nba, I'll keep it like that. If I differentiate cos omega t, I'll get minus sin omega t multiplied by omega again, right? The sin omega t, cos omega t is sin omega t, and then I need to differentiate the internal thing too. So then if I differentiate that, the internal function, then I get omega. Okay. So if I put it all together, my induced EMF is going to be equal to minus will become plus. So n b a omega and sine omega t. So this would be my induced EMF. Okay. So if I were to draw a graph for this, then I will get a sine curve for the EMF generated at any individual point in time. Okay. Let's see. when it is making an angle 0, a time equal to 0, when it is perpendicular, notice here, when it is like this, I told you that it's time 0, right? A time, I'm going to start now. When I told you, when it is here, all the maximum flux is going through it. Maximum flux is going through it. But what is the EMF? Because when it is here, the angle is 0. The angle is the angle of the normal, right? So the angle of the normal is 0. So at times equal to 0, E will be 0 because it is sine 0. But then, I want you to understand this. Maximum flux is going through it, but EMF is 0. Now, I come like this. I got here. Now it is flat. I told you, if you ignore this thickness, like it's a small coil, then we'll take just one loop, then no flux is going through it. The flux which is going through this area is 0. But notice that the angle will be here, 90 degrees, 270 degrees. Okay. Now it is from here 0 to 90 is what you got here. So when you get 90 degrees, then clearly, then you have maximum EMF. So when maximum flux is going through it, you have 0 EMF. When 0 flux is going through it, you have the maximum EMF induced. It's because that's when you are at 90 degrees. So the normal is at 90 degrees. This is when the coil comes here, you will have the maximum EMF. And then when the coil goes here, then you will get 0 again. Okay? And when the coil comes here, then you will get maximum, but it will be the negative thing in the other direction. I hope that is clear to you. Okay? So if you will draw the graph, it's like this. So this is 0 degrees, the normal, right? The degrees that the normal makes, normal to the coil makes. Then this is 90 pi by 2, and then this is 180 pi, and then this is, how much would that be? Okay, 3 pi by 2, and this would be 2 pi. So if I take one full circle, you notice it is here. Okay, 0, at angle 0, this value is going to be 0, and at here it's going to be maximum. Maximum will be sine omega will be 1, so this would be the maximum value, and B A W, that's the maximum. And when it is pi, make 180 degrees, then you get 0. Then here maximum. Here again N B A W. This time it's in opposite direction. Sine 180 is minus sine 3 pi by 2, 270 is minus 1. So you get a negative maximum minimum. How, in whichever way you want to look at it. Then it will become 0 again. So you have this kind of sine curve. In one cycle, then you get a curve like this. I want you to understand this. I want you to understand that when maximum flux is flowing through it, through the area, EMF is 0. When no flux is flowing through it, then you'll have maximum EMF induced, because that is when the change will be maximum. So EMF induced does not depend on the amount of flux going through. It depends on how much the flux is changing. See, from maximum, this change will be only, only slightly change. But here, from 0, even if you slightly change, the change is huge for a small amount of time. Okay, from 0 to 1 in 0.1 second is really huge. Okay, but from maximum, say 100 to 99 in 0.1 second would not be much. Okay, it's not much of a difference you'll get. Okay, so that's the reason. So the change is not much here, but here from 0, the change will be huge. So that it's a change that decides the amount of EMF, not the flux. That is what I want to drive at all the time. It's not the amount of flux that's going through it that decides it. It is the change, how much it changes, that's important. Hope this is clear to you. Okay, with that we will do example 6.11. Kamala pedals the stationary bicycle. The pedals of a bicycle are attached to a 100-turn coil of area 0.1 meter square. The coil rotates at half a revolution per second, and it is placed in a uniform magnetic field of 0.01 Tesla, perpendicular to the axis of rotation of the coil. What is the maximum voltage generated in the coil? Okay. So pretty much everything else is given. It is a straightforward application of the formula that we have. So she pedals a bicycle. So as she pedals a bicycle, then the coil rotates in a constant magnetic field. And how much rotation does it make? It is half a rotation per second. That is the frequency of it. And we have given you the magnetic field strength, the constant magnetic field strength, and also the number of turns and the area of the coil and everything. So now you need to calculate EMF. So what do we know? The EMF induced is 6.11, right? EMF induced E, we've just seen that it is N, B, A, W and sine omega t. So this is actually a function of time. So as time changes, EMF will change. Alternating current, we just saw that. So what's the maximum EMF? The maximum EMF will happen when sine omega t is 1. So that's what I want you to find. So this is, if this is 1, then you will have maximum EMF. Otherwise you will not have maximum EMF. You will have something less than that. Because sine omega t maximum value is 1. So the maximum EMF reduced maximum is actually NBAW. Okay, omega, I should say. So what is omega? Omega is actually 2 pi f. What is f? F is frequency. They said it makes half a revolution per second, which means that omega f is 0.5. So 2 pi into 0.5 is 1 by 2, so I'll get just pi here. Okay, so omega is pi radians per second. Pi radians per second. Makes sense. If you make half a revolution, pi radians per second. So that's what it is. Okay, so now E max is what's the number of turns? The number of turns is 100. So N is 100, N is 100. And what's B? B is 0.01 Tesla. 0.01 Tesla. And what's the area? Area is 0.1 meter square. So you got 0.1 meter square. That's the area. And what's your omega? Omega is pi. Okay. So what do you get here? So when you have 100 into 0.01, you get 1. 1 into 0.1, just 0.1 into pi. So that's going to be 0.1 into pi. That is equal to 0.1 into 3.14. So this is equal to 0.314 volts. So the maximum voltage you will get would be 0.314. So if we were to draw the graph, so it will be like this. So okay, this is 0.314 volts. Okay, this is E, and this would be minus 0.314 volts. Let's say, yeah, this and this. Okay, so now over here This is how the graph will look like for this. So that's about it. We'll look at the problems later.